Okay, so we're moving from what we did in the last video, which is kind of one-off payments at a future value or a future time, to a series of payments. We're going to start with discounting a series of payments over a 20-year period at €200 a year, and then we're going to use both discounting and escalation in the second stage and third stages of these calculations. So we've got a sum of money that needs to be paid out every year at €200 a year. We've got an inflation rate of 2.5% and we've got a discount rate of 5%. Now what we're looking for is the total present value. So what is this series of payments worth today if it is €200 paid out every year over 20 years at a discount rate of 5%. So I'm going to show you a few different ways of doing this first stage of these calculations without the inflation rate. Okay, so it's a fixed sum of money, whatever agreement you've made with a third party that you're going to pay them €200, irrespective of what happens in terms of inflation. So starting the calculations, I'm going to calculate a present value factor for each single year. So let's use the power of Excel to do this. And that's the calculation again, or that's the formula again, 1 over 1 plus n to the power of, or 1 plus r to the power of n. Just to delete what's there, equals 1 divided by open brackets, 1 plus discount rate 5%, close brackets, to the power of n, which is my first year, 1. Now what we're going to do is we're going to use the little dollar functionality which locks cells. The reason I'm going to do that is if I pull across this calculation or I copy paste it through the series of calculations, it'll move that 5% from cell to cell above, and I don't want to do that because then it'll move it into a blank cell. So if I want to fix a calculation, I hover over and I select C3 and I click F4, or I type in $C$3. So I'm going to click return, and there is my first factor. Now what I'm going to do is I'm going to copy, or I'm going to fill across that formula all the way across the series of payments. So little crosshair on the right hand side, once I meet it, or little dot, it turns into a crosshair. I'm going to click down my mouse key and I'm going to pull it all the way across, holding down my mouse key right the way to the end there, and there's my last factor. So it makes sense that this, I suppose, factors, or these single present value factors, are declining from year to year because they're discounting from year to year through that series of payments. Now what I want to do is I want to multiply my factor times my first year. So if I put €190 in the bank at the start of the year, by the end of the year I'll be able to pay out that €200 at a discount rate of 5% or an interest rate of 5%, whatever way you're kind of looking at it. If I fill that across all the way to the end, I've got my series of payments. It makes sense by the 16th year or even by the 20th year, if I put €75 in the bank today at an interest rate of 5%, because of the time value of money, I'll be able to make that €200 because that €75 is compounding every year over 20 years. At the end of the 20 years, I've got 200 left to pay out. So in terms of, I suppose, a net present value or an accumulated present value for that series of payments, I would click sum equals sum, and then I would highlight that series of payments, click enter. So 2492.44 or €2,492.44, and that is kind of a step-by-step process taken year by year. The one thing we got to look out for here is if we want to lock that cell, and I've done it by putting a $C in front of the column and a $3 in front of the row, which locks that cell, $C$3. I can lock columns and let the row flow, or I can lock the row and let the column flow, just depending on how you want to set up. That's a real handy little bit of functionality in Excel. Now I'm going to do one calculation for all that series of payments here using the net present value function in Excel, and this is very, very handy for this series of payments. So let's start it here. Equals net present value. So it tells you what that function does. It returns the net present value of an investment on a discount rate and a series of future payments. So let's open the brackets then. Let's select the discount rate, 5%. I don't have to lock it because I'm not bringing it all the way across. But what I do need to do next is I'm going to click comma, and then I'm going to select my series of payments. So I'm going to bring it all the way across to the end of that 20 years. So if I look at the formula, it's NPV C3, C9 through V9, close brackets, hit return. And that's the exact same calculation. It does it within the calculation as we did it individually up above. So moving on to the last way of doing this, and this is using the PV function in Excel. And this was quite similar to what we did in, I think it was the first one here, where we used the PV function, except I'm using it for a series of payments rather than a one-off payment. So remember when I said that PV function can be used in two different ways? Well, this is the second way. So starting it here equals PV, and PV returns the present value of investment, or the total amount of a series of future values, and that's the one we're using. So open brackets. The rate again is 5% because we're just using it once. I don't need to lock a cell. The number of payments, number of payments is 20 payments, 20 years. The PMT is the sum of money. So I can either click that cell, C9, which is €200, or I can just type in €200. So it's minus 200, just to make the calculation work. If I don't put in minus, it'll calculate it to a negative. And then I'm going to comma 0 because I'm not using the future value. That was what we did the last time around. And then I'm going to click comma on another 0, and the 0 is at the end of the period. So it's calculating the calculation at the end of each period rather than at the start of each period. And that does make a difference in terms of the factors that have been used. So that calculation was done a little bit different than we done it the last time in terms of how we used that formula. So let's hope this works. Brackets at the end, and click return. So there we have it, 3 different ways, kind of, I suppose, a section by section or a column by column way, and an accumulated present value across the series of payments, and then using the net present value and the present value functionality. Moving down from a series of payments without the escalation rate or the inflation rate to a series of payments with the inflation rate. So our payments of €200 are inflating every year at a rate of 2.5%. So the first thing we need to do is calculate what that inflation is on a factor by factor basis. To do that, we're going to use this simple compound interest formula, 1 plus I, being E really, the inflation rate to the power of n. So let's just get rid of what's in the box, equals 1 plus, and I am going to scroll up and select my inflation rate, the 1 plus brackets start, brackets at the end, and then to the power of little arrow 6 up to the power of the first cell. Now what I'm going to do is I'm going to, like I did previously, I'm going to lock that C2 so that it's not going to move. It is going to be locked at 2.5% and it's not going to move from column to column. But I want everything else to be fluid, so I'm going to click enter. So at a discount rate of 2.5%, it makes sense by the end of the year we're at 1.025 in terms of a factor. Bring that all the way across from year to year, and our factor obviously is increasing because our rate is increasing from a year to year basis. Okay, so that's our factor change. All we have to do now is multiply equals our factor multiplied by our cost. So €205 at the end of the first year, and bring that across from a year to year basis. For example, if I clicked on year 15, I would see as I moved, it would be 200 by 1.48 or 448, and that would be 289. So at the end of 20 years, our costs have escalated from €200 in the first year to $327.72 in the 20th year. Now what we're going to do, this is kind of a two-stage process, we're going to discount back per our discount rate at a rate of 5% and calculate what the factor is. So what we're going to do is equals, we're going to use the present value calculation. It's equals, again, 1 divided by, open brackets, 1 plus or being the interest rate or the discount rate, 1 plus or, and then to the power of n being the first year. Click. And again, I'm going to lock that discount rate. So I need to lock that C3. And there we've got our factor. So click and pull it across. I've already got some calculations in there and they are correct. So our discount rate, we double click, every year at an interest rate of 5% is discounting that factor 0.952, 0.907, 0.864, etc. all the way to the end. Obviously, if I increased that 5%, it would increase the value of the discount. So again, similar to what I've done before, now what I'm doing is I am calculating equals, multiply that factor by the escalated costs. So the logic of that is that it's escalated from €200 to 205 over that first year, and now I'm going to discount it back from 205 at an interest rate of 5%. So click enter, and it's now down to 105 to 2381. Let me move our decimal places back a little bit and bring that all the way across and let it do it for cell to cell right the way to 123.52. So if I sum those figures, sum the first number, so what's my total escalated costs for 20 years and a series of €200 a year? I get 5236.65. Okay, and what's my discounted cost? Is it equals sum all the way across, and hopefully this will work. Moment of truth, 3135 is my net present value for that series of payments. So in terms of the moment of truth, I suppose if I change my discount rate to 2.5%, that should come back to 4,000, and that 4,000 should be the equivalent of an inflation rate every year that brings it up at 2.5%, and a discount rate every year where it brings it back to €200. So that times 20 would give me 4,000. Now again, I don't want to do that, but that is my total net present value. Another way of doing that is, rather than doing it individually, implement the escalation rate and the interest rate in the same calculation or in the same factor. So this is a little bit trickier. Essentially, I have to manipulate or replicate this formula here. So let's try it. Equals, I kind of tend to do them bit by bit. Equals, open brackets, 1 plus the escalation rate is on the top, so I'm going to click the inflation rate. There we go. And I'm going to lock that inflation rate. Okay. And then I'm going to close it. And then I've got divided by 1 plus the discount rate. Okay, and then that's a bracket at the end of it. And then that calculation as a whole has got brackets outside it, I believe. Okay, I have to lock this cell too. So there we go. And then it's to the power of what will be the first year. So hopefully that'll work. Click. There's our factor, 0.976, that kind of takes account of the escalation up and the discounting back in the one factor. So let's see, does that work? Bring it all the way across. Okay. And that would work then for 6, interest rate. Okay, and then I'm going to multiply the factor by the €200, and I'm going to bring it across. And again, I'm getting a series of payments with different decimal places, so I could actually just bring them in to 2. And that works fine. And then I want to sum those and see, does that sum equal 313587? What's above? It's just done a different way. Hit enter. 313587. So it does. So irrespective of whether I do it in these kind of 2 stages where I escalate my series of payments or I discount my series of payments, or whether I do it in the one calculation that takes account of the escalation rate and inflation rate, or sorry, the inflation rate and the interest rate in the same calculation, it doesn't really matter. They're really doing the same thing. This is another way of doing it where I'm just going to use the NPV or PV series of calculations. What I need to do in this case is I need to calculate a real discount rate. So again, I've done this before, and it's not necessarily the difference there, 2.5% between the two. What I need to do is calculate the real discount rate using the real discount rate formula. It equals, open brackets, 1 plus I is my discount rate, close brackets, divided by 1 plus E is my inflation rate, close brackets, close brackets around that complete calculation, and then the last little bit of it there, minus 1 on the outside, minus 1. What does that leave me with? 2.4%, 2.44%. So it's not quite 2.5%, as in one minus the other. The real discount rate, which is calculated from the difference between the two, is 2.44. So let's leave that there and see what happens if I calculate a net present value for a series of payments. So equals NPV, open brackets, the rate is the 2.44%. Again, I don't have to lock anything here because it's just one calculation. So there we go. And the value or series of payments is, well, I can use the 200 there or this 200 series of payments across the top. Doesn't really matter. Okay, so where are we here? I'm going to close brackets and I'm going to hit return. And there we go. 3135. It's in pounds. So I could just maybe format painter that down there. Okay, so it's the exact same. It's just not going through that whole process. So it's doing the whole calculations in that very quick, easy formula there. Again, if I was using this PV functionality, equals PV, open brackets, rate again is the 2.44%, or the real discount rate, which is the equivalent to the 2. And my number of payments is 20 payments. My PMT, my payment amount, is minus 200. My future value, I'm not using that functionality because it's a series of payments, and my type is at the end of the year, so it's end of the year 0. Close brackets, return, and that's the exact same. Now it's probably, as you can see, a little bit easier using the NPV series of payments functionality as it is that PV series of functionality, but it's a lot easier doing this than it was doing these staged payments. So what's the reason of doing kind of staged payments? Well, you might want to show your escalated cost every year, and you might want to show your discounted costs every year. And you'll see in later examples that we do, we will need that. So that is that for the moment. So just moving down to the last exercise in this tutorial, and that is looking at irregular payments. We're going to use the same factors that we calculated up here, from a single present value, a yearly basis, also to the discounting, the escalation factors. So that factor and that factor. So what we're going to do is we're going to represent these costs firstly in real costs. So in the second year, let's say we got a payment of 200. In the fourth year, we got a payment of 200. In the sixth year, 200. In the eighth year, 400. Now this is more kind of applicable to life cycle costing, because these series of payments aren't usually uniform unless they're energy costs or cleaning costs or some sort of contractual costs that have been negotiated with a third party in terms of payments. A lot of the time they're replacement costs. Let's say, for example, like a door which might be replaced or repainted, at irregular intervals, and different things happening at different times, be it replacing the armoire, repainting the doors, replacing the seals. So here's an irregular cost here of payments. If I was to sum them across the 20 years, it would be the same as what I've done before. It would be a total cost of €4,000. Okay, what's my single present value calculation? Again, using the factors, I can click the first cell in my SPV row and equals, and let's use that SPV factor, which incorporates both the escalation rate and the interest rate. So I'm going to click that and multiply it by, well, the first item or cell has nothing in it, but I'm going to use it anyway, and click enter, and it's 0. But as I bring that across, I'll get payments or present values or net present values in each cell. So in terms of a total net present value across that irregular sum of payments, bring it all the way across, release it, and I've got €310. So I'm just going to click enter. Now I could do this in a kind of stage by stage process, whereby I escalate first. So let's try that. So equals, using the escalation factor, there it is there, that I calculated. Click enter, and multiplied by the first year, which there's nothing, I get 0. But as I bring that across, I'll have costs in those costs that are happening at that period of time. So €400 is €623, escalating at a rate of, what was it, 2.5%. You can see that one has got a cardinal number. It means that I'm going to bring it across to get an actual number in terms of its column width. So if I calculate the total escalated costs or inflation costs for that series of payments over the course of that 20 years, I would get, I would get 5,460. So in real money, in today's money, let's call it, that series of payments sums across that row and is 4,000. If I am escalating it every year, and that's why I'm using that escalation factor or simple compound amount, at a rate of 2.5%, what is 400 is 441, what is 800 in year 10 is 1024. Of course, if I change my inflation rate, my cost will change, and that's why I'm linking cells. The last series of payments here is to discount my rate. So I'm just going to get rid of what's there, because I want to show you rather than have it done for you. Starting with the first, so equals, and this was my discount rate. Because it didn't include the escalation, I'm doing it in a two-stage process, and I'm going to multiply that by the first item, which is 0. And that, of course, is 0. But if I bring it across and release, I've got costs that are discounting. In fact, I made a mistake there. I should have multiplied it by its escalated costs. So I'm going to drag that edge of that down. There we go. And then pull it across. So it really should be C24 in this case by C43, not that one, because I've actually escalated my costs and now I'm discounting them. So I'll bring that across now. And changes it slightly, and C does this cost equal 3010. So sum it. Start with the first year, pull it across, and release. And we get 3010. So from a logical point of view, just to kind of go back on what we did, this is our real cost, and this is our present value cost, with both the escalation rate and the discount rate in the same factor. And that's essentially what we did there. Okay, so using that formula over there on the right hand side that has the escalation rate and interest rate or discount rate in the same calculation. So that's why we did that. So it does it within the same factor, and that's why we've got 3010. Okay, this way here is doing it on a two-stage process. If I want to represent my life cycle costs as a nominal cost, well, what I do was I would multiply my costs by my escalation factor, make that calculation and drag it across. So my total escalated costs, escalating at a rate yearly at 2.5%, using those factors, gives me a total escalated cost of 5,460. And then what we're doing is we're discounting back. If I double click the cell, we're discounting back. Well, that's 0 there, but maybe I should show you the next one. We're discounting back that 210125, which was my escalated costs or my nominal costs, back with my single present value calculation, which is 0.907, and that one doesn't include the escalation. Probably completely confusing you now, but once I add all those items together, I got the 3010, and that is the finish of our second tutorial on life cycle costing, and we'll move on next week to something a little bit different. Thank you.